This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, very good morning to all of you. Yeah, So for all you have come in today, hopefully you'll stay with us for the whole semester, because usually the first lecture is, I see many of you, and then the second lecture, half of you disappeared. All right, okay. But that's besides the point, because you know all your lectures are going to be recorded. So for those who are not able to attend, you can still view them. But there's always, the dynamism of coming together in a class, and then it makes me happier. So because it'll be quite difficult giving a lecture to myself, right? Okay, now, so what we're going to do today is just going to be a very short introduction. So I'll try to wrap it up certainly within the hour. But I just want to give you a broad overview of the course. And of course, get you excited about solid mechanics, right? Okay, how many of you are excited about solid mechanics, right? Okay. Yeah, you're really excited. Okay, now, so this solid mechanics courses, some of you may experience it quite differently, because you may not have done some of the things that we're going to do in this course. Because from past experience, some of you have come in, especially through the Melbourne model, the pathway students. How many of you are pathway students here? Yeah, quite a few, yes. So you'll be exposed to finite element analysis, something that certainly, you have not done before, unless, you do this instead of, do final element instead of playing computer games, right? Now, so you won't have done this before. Some of you, they are coming from, lateral entry. You may have experienced FEA. Have you heard of final element analysis? Many of you have, some heads. Yeah, but again, we'll be doing some things that I'm sure will be quite different from, what you have done. Now, solid mechanics, I'll introduce you the team members very quickly. There's only one team member here at the moment, Aman, right? He's over there. So he will be your lecturer for the final element analysis portion. Right, we'll talk a little bit about stress analysis. That's where I try to instill a little bit of excitement that, solid mechanics is actually a very interesting course. Now, and then give you the course format, right, and then the course content. And of course, all of you are interested in how to pass exams and get a H1, right? So I'll give you some tips on how to do that as well. Now, so here are the lecturers, myself and Aman. The tutors, so Aman will also be tutoring Shaktik and Steph. So they are not here at the moment. One is in Canada. The other one, I'm not sure, probably flying back. Okay, so they've been attending conferences and things like that. Now, so these are the people in your team. Now, there will be a few people helping out during the workshop. Now, the workshop is fairly intensive. You guys will all be sitting in front of a computer, and there will be tutors going around. So there will be some new faces that will be helping you throughout the workshop. So please be nice to them. Now, so the next slide is a very important slide. All right, so if you are not paying attention since I got here, please pay attention. Now, the next slide looks like this. All right, so you see Aman, Shaktik, and Steph named there. All right, now, so if you decided during the course that I'm not too interested in them, okay, I'm not going to bother to meeting them, so you take them away, right? You are at a risk of failing this course. Okay, now I say this because what they are doing for you guys are extremely important, if not more important than me standing in front giving you the lecture. So these are your tutors, the person that will guide you through your workshop. Now, so of course you got your workshop, which is this bit here. Now that forms a huge part of your assignment. That's like 50 marks, okay? Now, you got all your tutorials. So Aman, Shaktik, and Steph will also be taking you through your tutorials. Now, if you decided, I don't have to attend the workshop or the tutorials, I guarantee you will bomb this course, okay? All right, so I'm just being very frank here. All right, so please work with us, and you will enjoy this course. I mean, I'm very sure you will enjoy this course, okay? So we put up, quite a comprehensive amount of materials here. Now, so don't just go to the exam hall and take the exams, okay? Right, you will be in trouble. Now, so why stress analysis, okay? Now, so this course is all about stress analysis. So if you want to sum up, what we are trying to do is you take anything, okay? I'll take this bit here, and I'm applying load on it, okay? I want to know what are stresses on my paperclip, okay? Now, how do you find that stress? You want a number. We are all engineers, right? We are interested in quantitative values. Okay, so you don't describe, the stress is a little bit high. Okay, not sure. You don't describe. You give a number. X Newton per meter squared or something like that. So now, why stress analysis? Okay, and I just want to show you a video and get you, say, excited about stress analysis. Now, how many of you know this plane here? Have you seen this plane? Yeah, this one hand here. Any of you heard it? There's another one. No? Heard? Yeah, some head. Right. So de Havilland, right, is airplane manufacturer. They're still around, right? But okay, when you talk about passenger aircraft, what do you hear? You heard about Airbus, Boeing, like the 737 MAX, right? Okay, right. So you hear about these two huge companies, Airbus and Boeing, but you don't hear very much about de Havilland, right? The Comet, Okay, have you heard about the Comet? The Comet is actually the first passenger airline, right, that came. Okay, it was really, really advanced at that time. Now, I'm just going to show you. So what really happens to the Comet is this. So it's the first jet airliner in production. They call it Yoke Peter. It flew in 1951. So this is many, many years ago, right? Okay. Now, so what happened is that in 1954, right, the airplane crashed. Okay. Shortly after that, that's in January, in April, right, another plane crashed. So from 51 to 54, right, they've been flying the plane, all was fine, and then one crash happened, and then another crash happened. And after which, right, you almost never heard about the Comet anymore, okay? Right, so something bad really happened there. Now, so I want to show you a video. Now, I'm going to have snippets of it because I don't want you to spend an hour watching videos here, right? Okay. So let's hope the sounds.
There's a spirit of enterprise. Civil aviation is booming, boosted by technological advances.
Let me see if I could. These things always happen, right? Okay.
It's the marvel of it.
I don't know why I couldn't get the sound on. But anyway, let's try this then.
The pride of Britain sends a message of superiority to every aircraft manufacturer in the world.
Okay, let's start again.
Has nearly doubled. 9:30 a.m. Sunday, January 10th, Rome Airport. Here, a dozen planes come and go every hour. On the tarmac stands Flight 781 en route from Singapore to London. The plane is a British-built de Havilland Comet. It's the marvel of its day and the perfect symbol of the new technological age. The Comet is the world's first passenger jet, and it's halving journey times around the world. The pride of Britain sends a message of superiority to every aircraft manufacturer in the world.
A dream comes true. At Hatfield Airport, the Comet, the world's first all-jet airliner. Begun 3 years ago, the airliner that makes every other passenger plane out of date will go into operation within 18 months.
The revolutionary design is based on de Havilland's hard-won military expertise. The plane is powered by 4 Ghost jet engines and carries 42 passengers and crew at up to 800 kilometers per hour, almost twice as fast as its nearest competitor. To help...
Okay, and then I'll take you down to... So now the plane has crashed. So the 2 crashes, right? So they are trying to investigate them. Oh. Wait. Technology. So. Yeah.
Explain why the second aircraft went down. Over the next 4 months, 781's wreckage is methodically pieced together at Sir Arnold Hall's headquarters in Farnborough. It's groundbreaking work.
Never before on that scale had an aircraft been reassembled by anyone, and the investigation team had to learn how to do it and develop the techniques and tools to reassemble a very badly damaged aircraft.
As they examine each piece of debris, they find intriguing clues. Bits of carpet, pills from the first aid cabinet, a corner of a mirror from the toilet, and scraps of passengers' luggage are all found wedged into the rear end of the fuselage, under the root of the tail fin. It suggests an explosion at the front of the cabin that blasted personal belongings to the rear of the plane. The question is, how and where did the explosion start? As the wreckage begins to provide some clues, so too do the victims. 4 of the bodies retrieved from the second crash are flown to Britain for post-mortem. The pathologist finds identical injuries to those of Flight 781, fractured skulls and ruptured lungs. Hall has a hunch. Could the entire plane have burst like a balloon? After all, the pressurized cabin designed to keep passengers comfortable would mean that the aluminium skin of the Comet is highly stressed. Any structural failure, and it might simply explode of its own accord. Such a violent decompression, as it's called, has never happened on a passenger plane before, but Hall and his team believe this could explain the terrible injuries. To test the theory, they stage a pioneering experiment. The team build a Perspex model of the fuselage, 1/10 the actual size. The cabin includes 28 miniature seats with 6 dummies. The model is housed inside a pressure chamber. When the pressure in the fuselage is increased to 8¼ pounds, the equivalent of flying at 12,000 meters, the team deliberately rupture the model. High-speed camera captures the results. The rapidly escaping air causes a tremendous release of energy. Seats tear apart and fly through the air. The dummies catapult vertically and smash their heads on the cabin roof. It's a graphic demonstration of a phenomenon experts like Paul Withy understand only too well.
The pressure cabin exploding is the same as a 500-pound bomb going off inside the cabin.
The experiment appears to explain how the victims of both flights sustained such horrifying head injuries. Not only that, the sudden change in pressure would cause the air inside the victims to expand rapidly, rupturing their lungs instantly. If explosive decompression can explain what happened to both planes, the team must discover exactly what caused the weakness in the structure of the fuselage. But a failure in the aluminium skin seems implausible. The manufacturer's own tests show the natural life expectancy of the fuselage is over 10,000 flights, many more than the number flown by the 2 crashed planes. Nevertheless, Sir Arnold is not a man to leave any stone unturned. He decides to put the entire airframe to the test.
Sir Arnold Hall decided that failure of the pressure cabin could be one of the possible causes. And because he wanted to make sure that everything was looked at, this was just one of the tests that was performed.
Before testing begins, the team look closely at the Comet design. They discover that to withstand the stress caused by repeated pressurizations, the skin of the aircraft must be immensely strong, but it must also be extremely light. In order to achieve this, de Havilland developed a lightweight aluminium alloy skin just over 0.5 millimeter thick.
The Comet's skin thickness was as thin as the designers dared go to withstand the cabin pressurization, and it was fixed by how little they thought they could get away with.
Sir Arnold devises a test to assess the strength of the plane's fuselage. The experiment is on a completely different scale to anything they have attempted before. It requires the construction of a massive water tank, measuring 34 meters long by 7 meters wide and 5 meters deep. Working non-stop, it takes a team of engineers 6 weeks to complete.
The team at the Royal Aircraft Establishment are working really hard. They're working 24 hours a day, they're working shifts, they're sleeping on site. They are a very dedicated team.
By May 29th, it's ready. The engines and cabin upholstery of a Comet are stripped out. The empty plane is gently maneuvered into the water tank, with the wings protruding on either side. Hydraulic rams move the wings up and down to simulate flight conditions. Engineers fill the tank and the plane with water. When they are both full, they force more water into the plane, pressurizing it as if it were flying. After 5 minutes, engineers reduce the pressure. Each test puts the same amount of strain into the aircraft as a single flight at 12,000 meters. Sir Arnold plans to test the fuselage to destruction. It could take up to 5 months. The experiment runs 24/7. Using 1950s technology, it's a grueling task.
Today we wouldn't do a water tank test. We'd actually use computer modeling and computer simulation to understand how the aircraft would behave.
As the tests continue, there are other lines of inquiry. In mid-June, 5 months after the crash of Flight 781, the team assembled 2/3 of the fuselage onto the wooden frame.
Okay, so they did that test, and eventually they came to a conclusion. So, please, when you're free, do watch it. So I want to show you what happened, right?
(1954). 26 minutes to disaster. Flight 781 takes off from Rome Airport. The plane is designed with an exceptionally thin aluminium skin. Rivets punched into the aircraft during construction create microscopic manufacturing defects. On each flight, the pressurization system puts enormous strain on the fuselage, causing stress to the skin, especially around the windows and doors. Repeated pressurizations turn the manufacturing defects into fatigue cracks that get bigger with every flight. 19 minutes to disaster. Flight 781 climbs to 11,000 meters. As it ascends, the pressure increases and the aircraft's skin becomes more stressed. At 10:51 a.m., the Comet's pilot, Captain Gibson, sends a radio message.
George Houghton from George Peter.
5 seconds to disaster. A fatigue crack reaches 2 centimeters in length, and the aircraft skin rips apart. At 10:57 a.m., the shattered pieces of Flight 781 fall from the sky.
Right. So this is quite a sad story, but it taught us something quite interesting. Now, so what happened if you look at the Comet plane that you saw earlier on? There are 2 sort of observation windows on the roof. Did you notice that? Right. So that's where the crack happens. And did you also realize that window is actually square? All right. Now, sometimes you wonder, why Yeah. Okay. And why do I say square, not circular? What happens if you got sharp corners? Right. You get stress concentration as well. Okay. So there seems to be quite interesting. Now because of something like this happen, we learn from it, and we will not do something that will jeopardize. Yeah. So if you get into a plane that's got square sharp windows, yeah, maybe you should be a bit worried about. Okay. Now, so this is how important, right? It is when we talk about stress analysis. So there are many cases. So I'll try to highlight them, throughout the courses, right? Throughout the course, you'll see bridge falling, towers dropping, buildings collapse, and sometimes you'll always wonder what happened there, right? Have you ever actually wondered what happened there? Recently, there's a balcony that collapsed in the World Swimming Championship, right? So you always wonder what happens there, okay? And then when you look back, right, it is down to the responsibility of almost maybe even just one person, of course maybe a team, and that person, right, could likely be you, right? Okay. Of course, if you decided to be, after you graduate, you don't want to be an engineer, then okay. But don't let me scare you, right? But just think about the responsibility that you have to uphold if you take up, an engineering position. All right. Okay. So it is an exciting area. Now, so this is what we will be doing throughout your course. You got this in your LMS, right? So week 1, 2, 3, 4, 5, right up to week 13. Okay, so the lectures are always going to be on, right? So you got 3 lectures, Tuesday, Thursday, and Friday, right? So we will run lectures right through the course. Your tubes and workshop, please take note, I'll show you later on, they don't come on too much later, especially the tutorials, right? Now, okay, so what we will be doing is in the FEA lecture, right, week 1, 2, and 3, we'll complete all the final element analysis lectures, and then with that, your workshops also start next week, right? Your workshops start next week. So you do the 2 together, right? They sort of designed in this way. Now, you will have an FEA test. Okay, that test will be in class. So all of you are going to come into the class, you'll be given a worksheet, and please, I know you all end up sitting quite close to one another, but we are quite serious about it. If you end up discussing, we'll just take the paper away from you, okay? So you don't want to lose that 10 marks. So we conduct the class in the room, right? And then we'll run that FEA test. So it's a simple test. It's really, to gauge your knowledge, all right, moving forward. Now, you're gonna get a work, okay, later I'll talk about your assignments. Now, so from week 4 onwards, right, you're gonna get lectures, right, and we'll talk about thin wall, flat circular plates, thick wall pressure vessels, rotating discs, and then we'll also talk about plastic collapse. Now, so when you look at all these topics, right, you have to relate to what you see. So now I encourage you nowadays when you go out, walk around, and then look out for circular plates, okay? Right, you could see it on the floor, you could see it on a building, or look out for a vessel, a pressure vessel, right? Like those beer container, okay? Now, look at them, and then ask yourself, what are the stresses inside those little things that you see, okay? Right, so think about it, as you walk around, and you see them all over, right? And every piece of materials there that's being placed, okay, and you're standing on it, you don't fall into the hole, it's because somebody did some calculation and said, yeah, it's fine, it could take your weight, right? Okay, now, so think about it, these are really almost like everyday structures that you see, okay? And then rotating this, every time you get onto your car, next time if you got a sports car, right, and then you ramp it up at X number of RPM, think about the centrifugal forces, right, on your, flywheel, okay? So, right, think about it. So now you are a mechanical engineer, right? Try to appreciate these little things that move around, that supports you. Okay, so this is what we'll be doing. Now your tutorial is going to start on week 5. Now, so your tutorial 1, 2, 3, 4, and 5 are, packed to your your lecture notes, your lecture. So once we finish the lectures, we will start doing the tutorials. Now, the tutorials is really, to be honest, it's really for you to pass your exams, okay? Right? Okay, so, there's always difficulties in gauging your knowledge. Okay, exam, I know some people say it's old school, but, it's a way to just make sure that, you are the one that is, being tested. So you have to do this, right? So we'll run through all the tutorials. So please, like say, be in tutorials. So any questions there? Any questions about lectures and tutorials? Okay? No? Yeah, so occasionally I know you guys are a little bit bored, okay? So I will show you some nice picture. So this is one. Okay? All right. So I do lead a quite an exciting life. All right. So this is in Annapurna. I just climbed it last year, right? No, I didn't climb Annapurna. I just went to the base camp. Okay. Yeah. Any of you been to Nepal? No. Oh, put it on your bucket list. It's one of beautiful place. Okay. Just 2 minutes. Now, so every time I show a picture, I'll tell you important information. Right. So now all your lecture notes have been uploaded on LMS. Okay, all PowerPoint slides have also been uploaded. Now, so I don't really use the lecture notes and PowerPoint slides in class. So what I do is I do what I call scribbles, okay? So I will take, an A4 white piece of paper, put it onto the projector, and start writing it. Among you do that? Yeah. Now, I think it's much more engaging, right? Because if I flash PowerPoint slides, okay, right, you all fall asleep. Okay. Now, so I really encourage you to come to class. Okay, we sort of work them together, and I think it works well because this course is pretty intensive. Looking at, taking it step by step. Because if I just flash the formula, I'll flash some later, right? Immediately you'll switch off. You'll say, okay, I'll figure out when I get home. And then, of course, when you get home, you got so many other things to do, right? Now, so we want to be able to work it through class, and then once you get out of class, at least you've got that knowledge behind you. Okay? Now, all lectures will be recorded, not the guest lecture, so please come for the guest lecture, simply because the materials, are not meant to be shared widely by guest lectures. All tutorial questions have been uploaded. Now, the tutorial answers, I will not upload them until after the tutorial, okay? So at least try to work them. All right, I know some of you may say, just give me the answers, but please, work with us, throughout the course. Okay, now, just let me talk a little bit more about the course. Now, all of you know what this is, right? All right, okay? You better know, okay? If you don't know, then you're in trouble. Okay, it's a pressure vessel, right? A fairly big one. Now, if I were to ask you, hey, can you tell me what are the stresses inside, here or here, right? In this direction, right? Or in this direction, right? Do you know how to calculate them? How many of you know how to calculate? If you don't know, I'm also a little bit scared, okay? Right? Now, have you seen this formula? All right, you've seen this formula. Okay, all of you familiar with this formula? Right, okay, so sigma is stress, right? Okay, you should know, right? Of course, H is hoop stress, and then you got the longitudinal stress. Now, you got this formula, right? So most of you, okay, when you are asked to say, hey, calculate the stresses on this pressure vessel, you will say, yeah, I remember saying some formulas, right? Okay, let me go and hunt down those formulas. And then you're likely, or some of you maybe even memorize them by heart and say that, yeah, no, these are the formulas, right? Okay, now, what if after you graduate, okay, you work as an engineer, and then, you work in a nice big engineering firm, and then your boss says, you're a new engineer, you must be really smart, especially from Melbourne University, all right? Okay, can you do the stress analysis for a structure that looks like this? Okay, what should you say? If you graduated from Melbourne University, you should say, no problem. Okay, now, So why? No problem. Or are you going to say, oh, where are the equations, for this structure? Okay, where are the equations for this structure? Now, so this course, right, is all about, figuring out from first principles. Now, so all of you say, oh, first principles, that's a nightmare, okay? But you have to know, derivation for first principles. Because if you don't know, right, okay, maybe before even I go there, what is derivation of first principle? Okay, so let's go back to this equation, all right? Do you know how this equation come about? Of course, they come about by some smart people, right? Okay, all right, okay, but you, want to be those smart people, right? You must know, or at least once you've done this course, how this equation, came about, all right? So you must derive this equation from first principle, okay? Now, first principle means take a little bit of material and then you worked it out, okay? And then eventually you end up with an equation like this where you can use, okay? Now, so let me just run through very quickly, right? So the thing here is ask yourself, where are the equations? Because you need them, right? Okay? So what we will be doing is the lecture will teach you how to derive from first principles. Okay, some of the equations that you may have already seen many times, even used it. Now then, we will arrive at a working formula. So I call this a working formula. Okay, a formula that you can use. All right. Now, then after that, you can apply it. Okay. Okay, that's where your tutorial comes in. Apply it. Now, so this is how you derive from first principle. Okay, you see all these equations, right, in your lecture notes. Right, we'll pick a piece of element and then we'll work through it, and eventually we'll come up with a set of equations. We'll reduce it, derive, and then eventually we will end up with a working formula. Now, so this step, this step 1 to 2, right, will be all dealt with during lectures. Okay, all right, okay. So I know some of you are a little bit, yeah. So it's going to be a little bit different. Okay. In other words, this step from 1 to 2 will also be in your exams. All right? Okay? All right? Now, some of you say, okay, you've been taking lots of exams and you always, just give me the formula, I use it. Right? Give me the formula, I use it. Okay? Right? But you have to know that, one day you'll not be able to find some formulas that you want to use. And then what then? Okay? Now, this is also aligned with your finite element course. Right, so you see that, like some of the really complex problem, you're going to use FEA. But bear in mind, I always tell students, in computer, rubbish in, rubbish out. Okay, so you still have to use hand calculation to at least, prove what you're getting. So we'll do that in the assignments. All right, and then finally, you have your application. So here is an application, a very simple one. Calculate, the pressure at your pressure vessels, right? And then you'll find numbers like, 75 megapascal, right? Okay, right. Now, FEA workshop and lectures, right? Any questions about course content? Okay, so far so good. Now, so this part is where we deal with very complex structures or, complex problems. Okay, so FEA, right, is a technique that we use a lot. Okay, if you graduate and go out and you say you're a mechanical engineer, and somebody says FEA, and then you ask them, can you tell me what FEA is? You probably won't get a job. Okay? Now, so please pay a little bit of attention because this is used widely, really widely. In my research, I use it, all the time. Okay? Now, so there'll be 6 lectures, 5 workshops, and students always say, oh, not enough. They want more. Okay, please just find time and go and use it. Okay, we'll be using Abacus. Abacus is a commercial software, so widely used in industry. Right. So now this session will involve presentation, demonstration, and then we get all your FEA code, Abacus, and then some exercise. Right. Now, bear in mind, right? FEA is 50 marks. Right. Okay. It consists of a mid-sem test, right? That class test. A workshop assessment where you sit in front of a computer and answer a couple of questions, right? And then you got your modeling project. Okay, this is your assignment. right? One, what the assignments will be, basically do a finite element analysis of the pressure vessel, right? And then also do hand calculations, okay? And then do comparison, all right? Okay. All right, any questions? Now, students usually do very well in this, okay? So, yeah, so I'll let Aman organize that once he start lectures on Thursday, okay, how that form is going to be like. So, your workshop, there's a 6 workshop now. So all of you are registered in workshops because there are quite a few of you. So we have extended that, okay? All right, so make sure you are, at the workshop. And then your assessment, all right? 10% mid-semester, 10% assessment, FEA workshop assessment, and then you get your 30% modeling and final exams. Okay, so it's not a hurdle, right? But please, some of you are quite interesting people. You ask me, oh, can I get, you actually, tell me, Frank, a lot of you like to know your marks before the exam, your assignment marks before the exams, right? Right. Is there a reason why you want to know?
Get a bit of idea about how much you need to pass.
That's a very honest guy there, right? Right, most of you will do well in your assignments, okay, if you put in the effort, right? But try to do. Students do this course. You can hit H1, right? Just work hard on it, okay? Right, it's not too difficult, right? Okay, now, so important dates, right? Okay, mid-semester test, workshop, and modeling submission. Okay, right, marks are taken off if you submit late without good reason. So please take note of these dates. All right. Any questions before I wrap up? So this is my contact. Aman will probably give you his email if he wants to when he starts his lecture. But if you got any problems, just drop me an email. Now the other thing is that I get lots and lots of email. So if you don't hear from me in say 2 days, please send a reminder. If you send a couple of times, I will surely reply. All right, okay, because I feel embarrassed. All right, but please just keep an understanding because I do get a lot of emails and it's always very difficult to answer them immediately or things like that. Okay, any questions? No? All good. Aman, you got anything you want to add? Okay, right. Okay, if not, welcome to Solid Mechanics, and hopefully we'll see you throughout the whole semester in class. All right.
I think I've got the same problem. honest, I like to enjoy this tutorial, but this now is too much with my
Yeah, don't worry, just go ahead.
But
Workshop is a little bit like different, so I just want to do the workshop. But tutorial is a class.
so I can know the spot of. Yeah, I mean like where it is if I don't know it.
Oh, you don't know where it is? If you look at the
The handbook.
if you look at the information sheet, right,